All right, welcome to West Virginia. Obviously not. I'm really struggling with this. Okay. Anyways, it is time for Joke of the Day because we know it's the best part of the day. I love Joke of the Day. So why doesn't the sun go to college? Well, because it already has 1,000,000 degrees. Anyways, let's brighten our lives by taking a look at negative exponents. Now recall that there are 7 laws of exponents, and we've already talked about 6 of them. This is the 7th and the last of the laws of exponents. So I want to take a look at where this idea of the rule for the negative exponents comes from. Because when you understand where rules come from, makes it so much easier, 1, to understand, 2, to memorize, and 3, to use. So let's take a look at where this law of the negative exponents comes from. So I want to ask, what does 2 to the 3rd divided by 2 to the 5th mean? And when I'm asking this, I'm saying, what does 2 to the 3rd in that numerator mean? Well, sure, it means 2 times another 2 times another 2. In other words, 3 2's being multiplied in that numerator. So then in this denominator, what does 2 to the 5th mean? Well, absolutely. It means 2 times 2 times 2 times 2 times 2. In other words, 5 2's being multiplied in that denominator. Now, we've looked before at this idea that 2 divided by 2 is a 1. In other words, those 2's cancel out to be a 1. So these 2's will cancel to be a 1. These 2's will cancel to be a 1, as well as these 2's will cancel to be a 1. So that means what I'm left with is a 1 in that numerator, and in that denominator, a 2 squared. Now, incidentally, 2 squared is a 4, so it is 1/4. But I'm more concerned about being able to get from here to here in one step. Now, recall, we also looked at our quotient property, our quotient rule, that said if we take a 2 to the 3rd and divide it by 2 to the 5th, when those bases are the same and we're dividing, then that means that we can keep the base because it's all about the base, We can keep that base of 2 and we can subtract those exponents, top minus bottom. And that would give us a 3 minus 5, and 3 minus 5 would give us a negative 2. So I'm looking now at saying, well, how would I compare this to this? How can I convert a 2 to the negative 2 into a 1/2 squared? In other words, if I come up with a negative exponent, how would I convert that into a positive exponent? And you can clearly see that if we would take this 2 to the negative 2nd power and we would put it over top of a 1, then all we have to do is take this fraction and flip it. In other words, take the reciprocal of it, and when we flip it, the 1 goes up to the numerator, the 2 to the negative 2 goes down to the denominator, and suddenly that exponent becomes positive. This is what we call our negative exponent property. The negative exponent property says when you have a negative in the exponent, what you do is you take the reciprocal. Take the reciprocal of that base. So when I take the reciprocal of b to the negative n, it's understood to be over a 1 now. So when I take the reciprocal, I will turn it into 1/b to the n. And notice what happens here is the exponent does not disappear. It does not disappear. It simply becomes positive. So I like to say that I take the reciprocal, or in other words, I flip it, or I like to say I shove it where it isn't. So in other words, if it starts up in a numerator, I shove it down to the denominator. If it starts in a denominator, say for instance like this, then when I take the reciprocal and I flip it, I shove it up to that numerator. And again, the idea here is I don't lose the exponent, it simply becomes positive. So let's take some examples of this. For instance, here with my 7 to the negative 3rd, that negative in the exponent means flip. As soon as you see in the negative in the exponent, you should immediately be thinking flip. So that means I'm going to take what is currently over a 1 and I'm going to flip it to be under a 1. And when I do, like I said before, I don't lose that exponent, it simply becomes positive. Now I do know that 7 to the 3rd means 7 times 7 times 7. I can evaluate that because I have more than just variables in there. I actually have some numbers. So 7 times 7 is 49. 49 times 7 is 343. So I get 1/343 for my answer there. Now notice in the second example, I have a to the 5th divided by a to the 8th. So once again here, when I am dividing those bases and they are the same, then that means I'm going to subtract those exponents. So I will keep that base because it's all about the base, and I will subtract those exponents, 5 minus 8. 5 minus 8 will give me a negative 3, and there again, as soon as you see a negative in the exponent, you should be thinking flip. So I'm going to take what's currently over a 1, I'm going to flip it and put it under a 1, and when I do, my exponent becomes positive. I don't lose the exponent, it simply becomes positive. Now, another way of looking at this is saying I have 5 a's up here being multiplied, 8 a's down here being multiplied, and as you saw up here, these 5 a's will cancel out 5 of these a's. You'll have 3 of these a's left over in that denominator. That is another way to look at it if you'd like. All right, so let's take a look at a few more examples just to make sure we get very, very good at this. Lots of practice will make us very good. Now notice in this example, into the 5th times into the negative 6. There's a couple of ways of handling this. One way is to say, well, I know my product rule said that when I multiply the bases and the bases are the same, I'm going to keep that base because it's all about the base, and I'm going to add up those exponents, 5 plus that negative 6, and that will give me a negative 1. But there again, negative in the exponent means flip. So I'm going to flip it and it becomes 1 over n to the first power. And now that my exponent is positive, I'm done. That is one way to look at it. But another way to look at it is to say, oh, negative in the exponent means flip, and go ahead and fix the negative in the exponent right from the beginning. I like to do that. I don't like negatives in the exponent. So as soon as I see them, I start flipping all of them. So that means I'm going to have an n to the 5th times a 1 over n to the 6th. Now what I'm going to do is you can either cancel in those diagonals, and these 5 n's will cancel out these 6 n's, leaving me with 1 in the denominator, or I can just go ahead and multiply straight across and get an n to the 5th over an n to the 6th. But here, like we had seen before, when the bases are the same and you're dividing the base, then you're going to keep that base because it's all about the base, and you're going to subtract top minus bottom, and 5 minus 6 will give me that negative 1 that I had right there. But there again, as soon as you see a negative in the exponent, you should think flip. And so that gives me back to that 1 over n. The nice thing that you're going to see about these laws of exponents is there's going to be several ways of looking at them. That as long as you're using your laws properly, you're all going to get to the same right spot. And that is a beautiful thing. It's so helpful. So let's take a look at this one. Now notice that it is a division problem. The bar means division. So I am going to divide 30 by 25, but it won't divide evenly, and I don't feel like dealing with those nasty decimals. So instead I'm going to simplify the fraction. What number will go into both 30 and 25? Absolutely 5 goes into both. 5 goes into 36 times, 5 goes into 25 times, so I'm left with a 6 on that numerator and a 5 on that denominator. Now I'm ready to deal with those variables, and this kicks back to some of those old laws of exponents that we're going to continually use. So you need to make sure you know those old laws of exponents. They're not going to disappear. We're going to keep using them. So when I deal with just these x's, because I need to deal with the same base, here again, dividing those bases when the base is the same, I'm going to keep the base, I'm going to subtract top minus bottom. So I'm going to keep that base of x because it's all about the base, and subtract 2 minus 1 gives me a 1. Now I don't need to show that exponent of 1, but that is what the exponent is. Now I'm going to deal with my y's. And notice again, when the base is the same and I'm dividing the base, I'm going to keep the base because it's all about the base, and I'm going to subtract 10 minus 15. Now 10 minus 15 will give me a negative 5. So what I have here is a 6 on that numerator along with an x and a y to the negative 5, and then that denominator of 5. But notice here a negative in that exponent, that means flip. Be very careful though, folks. You only flip the factor that has a negative in the exponent. Only the part that has a negative in the exponent. So in other words, this 6 to the first power, perfectly fine. The x to the first power, perfectly fine. They have positive exponents. They're great. So I'm only going to deal with this factor, or this part that has a negative in the exponent. That's the part that gets flipped. Or like I said, shove it where it isn't. Everything else is going to stay in their spots. This is going to get shoved where it isn't, so it's going to get shoved down to that denominator. So I will have a 6 in my numerator, an x in my numerator, a 5 in that numerator, and now that y to the negative fifth gets shoved down to that denominator. And once again, I don't lose that exponent, it simply becomes positive. And that is as good as that one gets, because I have all positive exponents and I only have an x and a y here. I cannot combine that y and my x because my quotient rule says it only works when the bases are the same. These bases are not the same. I can't do anything else with them. So let's take a look at this example. Again, a couple of the properties being used here. Notice that I'm taking an entire set of factors in here, raising all of them to the second power. Same thing happening down here. All of these factors inside being raised to the third power. So you know that this is my all-time favorite property. This is my power of a product property that says I'm going to take this and I'm going to distribute the power to every single factor that's inside. You thought I was done singing. I am not done singing. I'm going to get in your head and you are not going to be able to get me out. So I'm going to take this 3 and I'm going to distribute it to every factor that's inside. Now be very careful because yes, I distributed all the way through the parentheses, but only through the parentheses. I don't distribute beyond the parentheses. So my 26 that's out front is going to stay there. My 39 that's out front is going to stay there as well. Now when I take my 8 to the third and raise it to the second power, notice that this 2 being right up against the parentheses, that is my reminder that I'm going to take my 3 and I'm going to multiply it by 2. And I'm going to get a 6. So I'll get an a to the 6th power. Here, again, I'm going to multiply. 6 times 2 will give me a 12. And then here, I'm going to multiply those exponents and get an a to the 9th. And I'm going to multiply these exponents and I'm going to get a b to the 12th. Now I'm ready to deal with my quotient property because this is a division problem. And once again, I could take that 26 and divide by 39, but I'm going to get a terrible nasty decimal. I don't feel like dealing with that. Let's instead simplify the fractions. What will go into both a 26 and a 39? Absolutely, a 13. 13 goes into 26 twice. 13 goes into 39 3 times. So I'm left with a 2 on that numerator and a 3 on that denominator. Now I'm ready to deal with that quotient property that says when the bases are the same, I'm going to keep that base because it's all about the base, and I'm going to subtract those exponents, top minus bottom. 6 minus 9 is a negative 3, and now I'm going to deal with those b's. B to the 12th divided by B to the 12th. Well, since they're completely the same, they will cancel out. Or you can look at it as keep that base because it's all about the base, and then subtract those exponents. 12 minus 12 will give me a 0. But remember, one of those laws of exponents says zero exponent property says anything at all to the 0 power is just a 1. So this is just a 1. For that reason or the reason that they will cancel each other out. So now I am left with that 2 on that numerator, that 3 on that denominator. Aha, there's a negative in the exponent. And remember, I'm only concerned about the factor that has a negative in the exponent, only this one right here. And once again, that means flip. So shove it where it isn't. It started on a numerator, shove it down to that denominator. And when you do, it becomes positive. And here again, this is just a 1. I don't need to show that factor of 1. And there it is. And that's as good as that one gets. Now, let's take a couple of other examples where we're going to put all of our laws of exponents together. Now, let's recall those laws of exponents before we get into this, because we have 7 of them. And let's list them all up here just to make sure that we remember all of them. Enjoy that scenery, the lovely expanse of the universe behind us. Okay, laws of exponents state, whenever I am multiplying the bases, and the bases are the same, recall what that means is I'm going to keep the base because it's all about the base, and I'm going to add those exponents. On the flip side, when I'm dividing those bases and the bases are the same, notice that division is the opposite of multiplication, so the opposite of addition will be subtraction. These two go hand in hand. But again, it's all about the base, so I'm going to keep that base and I'm going to subtract top minus bottom. Again, if you know one of them, you pretty much know the other one, and that cuts your memorization in half. Now, when I take a power and I raise it to a power, notice that those sitting right beside that parentheses indicates multiplication. So I'm going to multiply those exponents. And recall my all-time favorite property that says when I have a product and I raise it to a power, I'm going to, what am I going to do? I'm going to distribute the power to every single factor that's inside. Oh, I just love it. And that goes hand in hand with the quotient here that is being raised to a power. Once again, I'm going to sing it again loud and proud. I'm going to distribute the power to every single factor that's inside. So I'm going to get an A to the N and a B to the N. And once again, cutting that memorization in half for you, these two go hand in hand. Then I've got my zero exponent property that says anything at all to the zero power is a 1. And recall that we've got 7 laws of exponents, and right now we got 2, 4, 6. Here is our last one, the negative exponent property that says when you have a negative in the exponent and you need to make it a positive exponent, all you have to do is take the reciprocal or flip it or shove it where it isn't, whichever way you want to look at it. So now, let's look again at just a couple more examples utilizing putting all these laws of exponents together. And we're going to see all the amazing things that we can do this. And I believe I am on, yes, letter F in the examples. And I'm going to take a 3c to the negative second, d, and I'm going to raise the whole thing to the negative third power. Now, what you might want to do is you might want to pause the video right now and give yourself a chance to work through this and see what you can do with it. Because what you're going to find is that there are lots of different ways to attack this example. Lots of different ways. There's probably like 5 or 6 different ways to do this. And some of you are going to start one way. Some of you are going to start an entirely different way. You're going to get to the same right spot. Some of you might start the same way, but in your second step, you're going to branch out and go in different directions from there. You're all going to end up in the same right spot if you follow these laws of exponents properly. So like I said, pause for just a minute, work this thing out, and then hit that start button again, and let's see where we go with this. So one way to attempt this is, like I said, as soon as I see a negative in the exponent, I say flip. So one way to do it is to say there's a negative in the exponent right here. That's going to take the entire parentheses, flip the whole parentheses. So I'll get a 1 over 3c to the negative second times d. But remember, when I flip it, I don't lose the exponent. It simply becomes positive. Now I could take a detour from there. One direction that I could take would say, okay, I see another negative in the exponent right there. I'm only going to concern myself with this factor that has a negative in the exponent. I'm going to flip it up. In other words, shove it where it isn't. When I flip it up, I get c to the second over 3d. Now I'm going to raise all that to the third power. However, a direction you could take from here would be to say, no, wait a minute. I think I would prefer just to go ahead and distribute the power to every single factor that's inside. So I could distribute here, I could distribute here, here, and here. Now when I do this, 1 to the third power is just a 1, but then when I do 3 to the third power, I'll get this, and c to the negative second to the third power, once again, right here tells me I'm going to multiply those exponents because it's right up against that parentheses. So negative 2 times 3 is a negative 6, and then I get d to the third. Now like I said, 1 to the third power is 1. 3 to the third power, 3 times 3 is 9. 9 times 3 is 27. And I get a 6 to the negative, or c to the negative 6, d to the third. But notice that right here, that negative in the exponent, if I deal with just this piece right here, again, that negative in the exponent indicates let's flip just the part that has a negative in the exponent, just the factor that has a negative in the exponent. So that will flip up, and I'll get c to the 6th over 27d to the third. Now, I cannot put the c and the d together. They are not same bases, so there's nothing I can do with them. Everything has a positive exponent. This is as good as that one gets. But let's go back to where we split and took that detour. What if I had left off right here? I took this detour right here, but here again, This means I'm going to distribute the power to every single factor that's inside. So I'll distribute it here, I'll distribute it here, and I'll distribute it here. Now when I take c squared and raise it to the third power, that right here says I'm going to multiply those exponents because right up against that parentheses indicates multiplication. 2 times 3 is 6, giving me c to the 6th. 3 to the third, recall, is 27, and then d to the third is just a d to the third. I'm getting the very same thing. Now, that's two ways of doing this. Another way to do it is to say, well, hold on a second. Right here, I would just go ahead and distribute the power. And that's perfectly fine. So I'm going to go ahead and distribute the power to every single factor that's inside. Now, when I do that, I'll get 3 to the negative third, c to the positive 6th, because negative 2 times negative 3 is positive 6, and then d to the negative third. Now here's where we tend to run into a little bit of trouble. Everybody's okay with the c to the 6th. Everybody's okay with this d to the negative third because people begin to understand, okay, the parts that have negative in the exponents I need to flip, and so they do fine to keep that c to the 6th up on the numerator, slide that d to the third down to the denominator. Here's where a lot of people run into trouble. You need to remember, guys, a negative in the exponent means flip. Flip, 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 flip. A negative in the exponent does not mean, excuse me, negative in the exponent does not mean slide that negative down front. So it's not going to mean negative 3 to the third. Now a lot of people do know 3 to the third means 3 times 3 times 3, which is 27, but a lot of people will give me a negative 27 c to the 6th over a d to the third for their answer. But see, this is a positive 27, plus that 27 is in the denominator. So you need to remember, yet again, you've got to understand, negative in the exponent means flip. Flip. It does not mean slide that negative out front. So therefore, once you hit here, this part will get flipped or shoved where it isn't. This part will get flipped or shoved where it isn't. And when that happens, you will land on a c to the 6th in the numerator, 3 to the third in the denominator, d to the third in the denominator, and like I said before, 3 to the third is going to give me that 27 that I wanted right in there. So you can see there's several ways to attack this problem, and notice that even though you might have all started this way, and then you branched off from there, or perhaps you distributed your power through, or some people right here would go ahead and flip that c from the beginning. Some people, let's go ahead and write that one down here, they would have a 3d and go ahead and flip that c down to the denominator right from the start like this. And then they would distribute the power all the way through, giving me a 3 to the negative third, d to the negative third, and then c to the negative 6th. Negative in the exponents in every one of these, so you're going to flip everything. The c to the negative 6 will come up, 3 to the negative third will come down, d to the negative third will come down. That'll land me right back here, which will take me right back here. Or, right here, you could go ahead and say this negative in this exponent means flip the whole thing. And if I flip the whole thing and it becomes positive, that's going to put me at c squared over d to the third, and that creates this exponent as positive, taking me back up here. But again, I'm going to distribute my power all the way through, landing me right down here yet again. So like I said, I just described about 6 different ways to solve the very same problem. But I used my laws of exponents all properly, and therefore every one of those examples or every one of those routes that I took got back to the same one right answer. It's a beautiful thing when you've got lots of options like that. So let's take a look at one more example just to make sure we're very, very good at this. And I'm going to keep it on this side instead of flip it over because I like having my laws of exponents sitting right here in front of me that I can refer to. Now you will have to have these laws of exponents memorized. It's very important that you've got them memorized. But I like to refer to them right here as I'm going through the examples. So I've got a 6x to the 7th over a 2x squared all raised to the negative 4th power. Once again, I'm going to show you that there are multiple ways of doing this. One way, and what most people do, is they go, okay, all right, distribute the power, because you can't get me out of your head no matter how hard you try. And so they'll say, well, I'm going to distribute my -4 here, 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 and here. That will give me a 6 to the -4th, x to the -28th, because remember, right up against that parentheses indicates I'm going to multiply those exponents. 2 to the -4th, x to the -8th. And then a lot of people say, whoa, there's negatives everywhere. I'm going to flip the whole thing. And so when you flip the whole thing, you get 2 to the 4th up on the numerator, x to the 8th up on the numerator, 6 to the 4th on the denominator, x to the 28th on the denominator. Now from there, 2 to the 4th, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and I have an x to the 8th. 6 to the 4th, 6 times 6 is 36, 36 times 6 is 214, I believe, and times 6, in other words, 4 6's being multiplied together is 1,296, x to the 28th. From there, we'll simplify. 16 goes into 16 once. 16 goes into 1,296 81 times. And now, my quotient rule right here says when I'm dividing bases, and the bases are the same, I'm going to subtract those exponents, top minus bottom. 8 minus 28 will give me a -20, so I have an x to the -20 over 81, and there's that negative in the exponent, which indicates flip. So I'm going to shove this part down to that denominator. That leaves me with a 1 in that numerator. And there's my answer. Now, detours that you can take. One detour is to be able to say right here, a negative in the exponent immediately means flip. So some of us are going to take this whole parentheses, flip the whole thing from the very beginning. Now if you do that, then you get 2x squared in your numerator, 6x to the 7th in your denominator, and recall, I don't lose the exponent, it simply makes it positive. From there, a lot of people like to distribute the power. So they'll distribute here, 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 and here, but notice that gets you right up there, and then you can continue to run with it. Another option, and my favorite option that a lot of people don't see, is right inside the parentheses. Notice that 6 divided by 2 is just a 3. In addition, x to the 7th divided by x to the 2nd, well, they're the same base, so I can subtract those exponents, and 7 minus 2 will give me a 5, so I get an x to the 5th. Oh my goodness, that is so much easier to deal with. I have just shrunk down what's inside the parentheses. Much, much easier. So at this point, I have a couple of directions I can take. One is to go ahead and distribute the power to every factor that's inside, giving me a 3 to the -4th, x to the -20th. And then because I've got negatives in both of those exponents, recall negative in the exponent means flip. So shove that down to the denominator, shove that down to the denominator. When you shove that 3 to the -4th down to the denominator, you'll get 1 over 3 to the 4th, x to the 20th, and 3 to the 4th. 3 times 3 is 9, 9 times 3 is 27, 27 times 3, sure enough, right there, 1 over 81, x to the 20th. The other detour that you can take, right here, that negative in that exponent, again means flip, so I can take this 3x to the 5th, which is currently over a 1, and I could flip it so that this comes down to the denominator, and when I do that, I'll have 1 over 3x to the 5th, and remember, I don't lose my exponent, it simply becomes positive. Now I'm going to distribute the power to every single factor that's inside. So I'll distribute it here, I'll distribute it here, and I'll distribute it here, which will take me right back to there. And 3 to the 4th is still an 81, still taking me to the same right spot. So again, I have described here about four different ways to solve the very same problem. And I'm getting to the same exact one right answer because I'm using my laws of exponents properly. And it's a beautiful, I cannot stress enough how beautiful it is when you have choices like that and options like that, as long as you're using your laws properly. So you can go where your mind will take you, as long as you're following these laws. I hope it helps. Have a great day.